Good afternoon, everyone. So we are going to continue our discussion on combined loads. We didn't finish the problem. As you can see, I tried to write something there so to make everything fast because I tried to review what are the remaining topics that we need to discuss so that we can cover some of the topics that will be covered in the midterm exam, in the final exam. So I think we are a little bit behind. So just a reference to the next activities for this course. On March 3, which is next week, 1 week from now, you're going to have quiz number 3 during class hours from 1:30 to 2:30. So you have 1 hour. Normally it's 50 minutes. Again, I added 10 minutes uploading time so that you will not be rushed whenever you scan or take a photo of your quiz. Now, midterm exam is on the next meeting, March 19, unfortunately, which is a 3 hour exam. Our class is scheduled 1:30 to 4:20, so I put 4:30, but if you have any conflict, just let me know. But I put a 4:30 to add 10 more minutes, but if some of you have problems with that, just please let me know so that we can make some arrangements for that additional 20 minutes. Now, quiz number 4 will be after a week after quiz 3 and midterm exam, which is March 24, class hours. Now, just so you will not be pressured to submit like super in time. So I made this kind of I would say adjustment for quiz number 3. So you are allowed to be late up to 15 minutes in either quiz 3 or quiz 4 without any deduction. So let's say if you feel that you need more time in quiz 3, you can be late 15 minutes. That's okay, but it should only be once. It's either quiz number 3 or quiz number 4. It should not be both. So I have a situation here. So let's say if you are late by 10 minutes in quiz 3, you will not get deduction. That's okay. But you must submit quiz number 4 on time to avoid deduction. You cannot transfer the remaining time to the other quiz. So it's just up to 15 minutes. It's not 15 minutes. So again, you can submit it late. But the exam will be designed to for you to answer it within 50 minutes. So it should not be a problem, to be honest, in terms of finishing it. But again, this I made this one so that you will not be too pressured to submit it just in time. But I advise you not to use it unless you really need it. Just use it during the last quiz. I think that's the safest way. Try to finish quiz number 3 as fast as you can. So there's a message then. Yep. So yeah. So yeah. Again, I know that some of you might have some pressure submitting it and might be worried that you're late. But yeah, that's why I'm doing this one. Now we don't have much time. As much as I want to discuss everything with you, I'll just upload the solution. But again, book a time with me if you have any question, if you have any problems. So quiz number 2 solution will be uploaded on March 13. That's a Saturday, maybe tonight, but I put 13 because I have tons of things that I have to finish by end of this week. So I put 13, but I might upload it later tonight. So quiz number 2 solution will be uploaded on the 2L. Quiz number 3, because it's very tight. Quiz number 3 to midterm exam, it's just 2 days. So I'll upload the solution so that you can review the mistakes that you might have done in quiz number 3. I'll upload it March 17 in the evening, so I still have at least 2 nights to review the mistakes that you did in quiz number 3. And on Friday, which is March 12, unfortunately, I have an important meeting from 2 p.m. Maybe that would be for 3 or 4 hours. So as much as I would like to cancel that lecture day, we are behind. So I'll do a 30-minute lecture that day on Friday, just 1:30 to 2 o'clock. I'll dismiss you by 2 o'clock because I have an important meeting to attend at 2 p.m. That's why your 2-minute pitch will be handled by your TAs, Navid and Chris. I won't be there, but it will be recorded. My name might be there. I'll just join so that to allow them to record the pitch. But I won't be physically there. I'll just join using my phone probably. So just so you know that I won't be there in ME 2125. I know not all of you are enrolled in ME 2125, but this is just to let you know that your TAs will check the attendance and will facilitate the 2-minute pitch. Now, deliverable number 3 for that day is up to 11 p.m. It's not constrained to class hours, so it's up to you how you want to work. But this is Friday night. I don't suggest you uh, to uh, uh, to make your Friday night as a working night for this. But maybe yes. But I put 11 p.m. as a deadline for, and this is deliverable for. Sorry, this should be 4. I made a mistake. This should be 4. And I sent you a message via MS Teams in 2125 groups. You know what to submit right there. I can send it again, or if you have any question, just send me a message. Not right now because our time is a little bit tight for 2122. But if you have a message, just let me know regarding ME 2125. So again, this will be scheduled. This information are uploaded on the 2L in the lecture slides. So that's lecture 22 to 25. So yeah, there you go. Any questions so far? Everything is clear? And all,
Yeah, Professor.
yeah, go ahead. Yeah.
I see right there the quiz is March 24th, but on the syllabus it was on the 31st, I believe.
Oh, okay. So I made a mistake. That should be 31st. We should follow the syllabus. Yeah.
Okay, so it'll be the following Wednesday.
Yes. Yeah. We'll stick with the syllabus. So sorry, guys. That's 31st. Yeah. Thanks for pointing that out. Yeah. Okay. Okay. Any other question? Again, this is okay. Any other question, class? Just so it's clear. It's 31st. Sorry. Okay. Okay. Any question? It's good. Okay, so if we don't have any question, now let's continue our discussion about combined loads. The practice problems for quiz number 3 is uploaded on B2L. It will be design of transmission shafts and combined loads. And then there's also guide for midterm exam. Basically, it's just all the practice problems from quiz number 1 to 3 with some additional topic about deflection of beams, which we are going to discuss today and Friday and hopefully by Monday. But it should not be too complex, I would say. But again, let's see. Go back to my lecture. Okay, so now let's continue our discussion on combined loads. So basically for combined loads, we have different moments, different forces aligned along X, Y, and Z. Okay. So we have X, Y, and Z. So we have different forces and then different moments. And our objective is to resolve those moments and forces at a certain point. In this particular case, it's at point K. And then once we get the cross-sectional area, we can slice it into different moments, different forces, and all the other things, which I'm going to discuss later on the right side of your screen, wherein we have those drawings of forces and moments. So we solve this particular problem here. We started to solve it. We're almost done. But so looking at this notes on the right side, and you can see my handwriting now, it's good. I want to write as clean as much as possible, but ME 2125 is just 50 minutes. So anyway, so as you can see from here, so let's say this would be your part. That's your cylinder. And take note that we take the cross section area of this section here, H and K. So that's H, that's K, but we are more particular with point K. So we slice it so that we have a cross-sectional area. So now we have this cross-sectional area. Now, once we have a cross-sectional area, you have 3 different forces aligned along your X, Y, and Z. So your X, just this. Okay, so that's your X, Y, and Z. Now, you also have moments along that axis. So technically, you have 3 or 6 numbers that you have to think about and what would be the effect of those in normal stresses and shear stresses. Now, what we did in the previous lecture is we calculated those numbers, and that's the one on the right upper right side of your screen. So you have, for example, the torque is 900 Newton per meter, or Newton meter, 750 Newton meter, and your M sub Z is 1080 Newton meter. So all of them are positive. That's counterclockwise rotation, looking at the positive direction of that specific axis. Now, we also take different forces. Our P, which is aligned at X, is equal to negative 15. V sub Y, which is shear at shear force at Y, is 18 kilonewtons, and we have shear force in Z is equal to 0. So we calculated it last meeting. I just summarized it on the upper right side. Now, look at this purple line here. So you have torque, moment in Y, and moment in Z. Now that's your three different rotation and three different axes, and one of them is torque because that's the axis which you have which is perpendicular to your cross section. In this particular case, you can see that this circular section here is perpendicular to your x, which means whatever rotation in my x, that would be my torque. So I can see it as my torque. Same thing for this blue parts right here. Your P, V sub Y, V sub Z, they are your forces, but one of them is perpendicular to your surface. So if this is your surface again, water bottle, so the surface, that's perpendicular to that one, that's your P. And the other two directions are parallel to your surface, and that's your shear force, which are Vy and Vz. Now, the question here is how can we determine if the moment applies generates a normal force or not. So let's look at this because we are particularly interested in point K. If we look at the projection of point K, so your point K is in the axis. I'm just looking, where's point K? This is X and Y. So this would be your point K, and that's X and Y axis. Now, at point K, so for normal stress, we know that this, as we discussed last meeting, this your P and your moments creates a normal stress. And how can I say that that creates a normal stress? Go back to your equation for your normal stress. If you look at down below, I'll encircle that one. Your normal stress is force divided by area, or MC divided by I, which means my moment can generate a normal force as well as my P, which is my force per normal stress, which is and your P is my force perpendicular to the surface. Now, if we look at our normal force, the first thing is P is very obvious. P should be very obvious to you that this is my cross section. I'm pulling it this way. That's my normal stress, and normal stress force divided by area. So that's my normal stress P. That's pretty straightforward. How about for moment, which is not super straightforward? Let's say you are projecting point K in Y and X axis, which are this one and this one right here. And your K is right here. And how would I check it in my axis? So this is Y, this is X. I'm looking at my Z. And if I'm looking at my Z, I'm seeing my K as this one along the center line right here. Now, in my projection of my X and Y, I can see my moment in Z. That's my rotation in Z. If I if I apply moment in Z, I'm pulling from this side, a lower section of my cylinder, and this is a cylinder, just so you know. And then this would be the cross section. Once I have MZ, I'm pulling it and then pushing it right there. If it's counterclockwise, in our case, it's counterclockwise. If it's clockwise, of course, it's the other way. What do you think would be the effect on point K? Nothing, right? Because there's a tension at the lower end, compression on top, which means at the middle, there's no tension or compression. It's neutral zone right here, which means your M sub Z at this particular point doesn't contribute to the normal force. Whatever M sub Z you have, it will not contribute to the normal force. Now, let's look at the other M, which is M sub Y. Where is M sub Y? So if we look at M sub Y, we have to look at the projection on the plane that doesn't contain Y, which is X and Z, because we are talking about rotation in Y. Now, if we look from the top, so we're looking from the top, we do the cross-sectional area here, we can see that point K is at the very edge, which is this guy right here. So it's at the very edge right here. Now, I'm looking at the effect of my M sub Y, which means that it's rotation in Y, and this would be this rotation because this is X, that's Z, and then the rotation along Y is that one, which means if this is my point K at the bottom of my cylinder, I'm pulling it right here and then pushing it on top, which means I'm pulling my K if it's counterclockwise rotation, which in our case, it's counterclockwise, it's positive based on our answers in in the previous lecture. So which means that if we are going, any questions about that, any confusion about that? So I want this one to be clear so that everyone would be on the same page. Any question? Okay, it's clear. Okay, so which means that your P and M sub y has an effect in point K. But whatever number you have for M sub Z, it doesn't have an effect because your point is at the center. It doesn't give you a normal stress. So which means that if I'm going to, so we are analyzing point K. So let's go back again to point K. And at point K, we have to analyze it in Y and X. So that's Y and X. And if you imagine, for example, your stress that's generated by P, and let's write it down, M sub Y, you know that this will not contribute to any of your normal stress. There's no other way. Now, your stress in the X direction, because this would be your surface, I'm pulling it right here with my P. So my stress, my sigma X, and it's not really pulling it. Your P is pushing it based on our direction. Your P should be the other way, pushing it compression, which means that I have negative P divided by A. So that's a compression. I'm compressing my K. Now, I can, if you want to be more organized, you can write MZ for now, MZ, MC divided by I, let's say, plus MY C divided by I. But again, this has no effect as we discussed earlier because it's at the center when we're talking about M sub Z. How about M sub Y? We know that M sub Y is a counterclockwise rotation, which means at point K, I'm pulling my point K and then pushing it right here, which means it's a positive number. So here you have to be very particular if you are adding two normal forces or you are subtracting them from each other. Now, that's your sigma sub X. I can now substitute my numbers. I calculated my area. Take note that in step number 8 in previous lecture, I have a numbers here. That's number 8, that's number 7. Take note in the previous lecture, we numbered the different steps. And in step number 7, we calculated the area, calculated I, we calculated J. We have those numbers from the previous lecture. So what are those numbers? I'm going to write it shortly. So here we have 15 kilonewtons divided by 1.257 times 10 negative 3 m squared. So that's that one we calculated before, and that's 0 plus, or you can just remove that one, plus 750 kilonewtons meter, I think. And then your C, yeah, you should be able to see this, but I'm going to flip it up, 0.02, and that should be in meters. That's the radius of your section. It's given right there. You can see radius is 20 millimeter, but we are converting everything into meter. So we have 125.7 times 10. I can't understand my handwriting. And raised to 4, and that will give you a sigma X, which is equal to negative 119 plus 119.3.
Professor, is that supposed to be times 10 to negative 4 meters cubed or 4?
Which one, sorry?
The one MYC over I, when you're writing those values down, 125.7 times 10 to the
negative 9.
Negative 9. That makes more sense.
Okay, sorry. Yep. Okay, sorry for that.
And then meters to the power
meter
of
4. Yeah.
Yes. Thank you.
Okay, that's okay. I can't even understand. I have to look back, so that's okay. Okay. So
Professor, sorry.
Yeah, go ahead. Yeah.
What is 750 Newton per meter when we calculate it, not kilonewton?
Oh, yeah, that's true. That should be meter per. Let's go back. Yeah, Newton meter. I only have 70. Okay, yeah. or I think or 0.7 if you want, but you have to be consistent with unit. But yeah, thanks for pointing that out. So that should be Newton meter. And I'm happy because you are particular with details, which means that you can still remember our discussion from previous lecture. Any other question? Good. Okay. So let's get this done. So, okay, so we have this 11.9 negative, that's positive 119.3. And that gives you a sigma x value, which is positive 107.4 megapascals. So which means in this particular case, I have a tensile force along my K, along my X. So I have sigma X, which is equal to 107.4. But that's normal stress. We have to calculate for our shear stress as well. So shear stress, and this one becomes a little bit more complex, not much. Now for shear stress, you are looking at your torque. You're looking for V sub Y and V sub Z. Now, let's analyze this section here. It's the three-dimensional. Now, our torque is counterclockwise looking from the positive value of Rx. So it's counterclockwise, which means if I'm looking at my cross-sectional area, so let's say this is Y and Z. So my torque is like this. And I have this as my point K. Now, if you imagine point K, so this is Y and Z, but you have to look in Y and X. So I have to imagine Y and X, and I have to look at my element right here. Now, if I'm rotating counterclockwise for my torque, counterclockwise, you can imagine that I'm going from positive value of X to the negative value, positive value of Y to the negative value of Y. I'm pushing my K, or I'm providing shear at my K, this rotation right here, this rotation, and that rotation is this one right here, from positive Y to the negative Y, which means my torque is providing this shear. So that would be the shear stress for my torque, correct? So which means my contribution of my shear for my torque is a negative value. So I'll just put negative there for now. So I have, So I have my torque is a negative number right here. Now, how about my V sub Y and V sub Z? So let's go back to our cross section. It's not a good circle. Okay, so now let's imagine this, and this would be your Z axis, Z, Y. Let's first look at the Y axis, Y. So this would be our point. I'll change the color. This is the point. Your V sub Y is a positive number, which means it's going up. That's what we calculated before. And how would you know it's going up? You can see this is just your V sub Y, P sub 2. So that's V sub Y going up. And it's going up like this. So that would be your V sub Y. That's kind of your stress along your V sub Y. That's your V sub Y. Now, remember, what's the equation for shear for V sub Y? It's VQ divided by IT. We know this one, which is T, which is just your just the diameter of your section. That's the thickness of the section. So this is just basically your diameter. Your V, that's the value of your V, you know. We calculated I. It should not be a problem. How about our Q? Our Q, as we defined, is, so if we're going to take this point right here, area above that point, which means if we talk about area above that point, we are talking about perpendicular to our shear force, and then this would be the upper area that we are talking about, which is just half of our circle. But the problem here is our Q. Remember, our Q is equal to the area times the I can call it X, but your X is distance of centroid to the, I'm not sure if you can read this one, neutral axis. So that's your x is a distance of centroid to the neutral axis, which means I have to get the centroid of my circle, which should not be a problem as long as you have an equation for that. So let's say your centroid could be somewhere here. Yeah. But again, the equation for that is I'm going to write is y bar is equal to, oops, I should not stick with the orange one. Should go back to black. Y bar is equal to 4c divided by 3 pi. And what you're going to measure here is this y bar here. So this would be your y bar. So now it's just the area of the half of the circle times your x. If we're going to calculate this one, but this is not the tricky part. The tricky part is, but anyway, let's calculate first q so that not to confuse you. So first thing is, so your area is equal to 1/2 of pi r square, which means that so that's the area, and then your distance to your centroid is y prime. So I can just multiply this two to get my q. So I have q is equal to a times y prime, for example. I use x here because the distance sometimes is along the x, along y, but doesn't matter as long as you know. You have to be very particular with your area. If your shear, which we're going to discuss later, if your shear is going up like this, the area you're going to are talking about is above and below, which is because your shear is going this way. Anyway, let's go back to this one. So we have q, which is equal to 1/2. And you can calculate this one if you want for practice. 3 pi. And c is equal, so you know that your c is equal to, let's not put c. So I'll put the value of q because you know what's the value of c, and your q is 5.33 times 10 negative 6 m cubed. Take note your t is equal to 2c. What do I mean by t? It's just going back to this equation here. So now I have all the values that I need, but I won't calculate yet. I'll just keep the numbers right here for now because I know the effect of my torque. I know the effect of my v sub y. How about the effect of my v sub z right here? V sub z is 0, but it could be a non-zero value. But let's look at, if it's a non-zero value, let's look if there's an effect for our v sub z. Let's draw the section again. So I'm going to write cross section again.
For
Yeah.
q, it's 5.33 times 10 to the negative 6.
Yes.
Okay,
Yeah.
thank you.
Yeah, thanks. Yeah, that's negative 6. Okay. So this would be, let's say, y and z. And the second shear is v sub z. So which is your v sub z is like this one. I'm thinking should be the other way because it's positive. Yep. And it's 0. So it could be any direction. But let's say your v sub z is around this direction. So that would be your v sub z on this cross-sectional area. Now, if you're going to look at this one, so let's say your point h or point point k, we're using point k. Your point k is right here. Now, if your v sub z is a non-zero value, of course you can calculate this as vq over it, let's say. Now, how can I calculate my q in this particular case? So my q is along, I have to look above and below, but it should be along the direction of my shear, which means the above and below area that I'm talking about is this area right here. Which means that if I get my q, so my q, as we discussed from above, is area times y bar, I will get the area of my whole circle, so that's not a problem, multiplied by the centroid, and the centroid of that circle is this, the center of the circle, and that's the distance from the centroid axis, and this is the centroid axis, so this becomes 0, which means that if your v sub z, even if it's non-zero value, in this particular case, let's say, it would always be 0. It has no effect at your point K. It would not give you any shear stress at point K based on this loading condition right here.
Professor, could you explain that part again? I'm not sure I follow why there would be no Q.
Okay, yeah, sure. So let's say the definition of your Q is the area above that above your the point of interest. So if we go back right here, so your point of interest is right here. That's the one that you are analyzing. That's point K. Yeah, so that's point K. Now, if that's the area that you're analyzing, you want to take the area above that point, which means area above or below, to be honest, but it's, let's say, area above, which means if I have this K, my area above that we are talking about is this one. Now, how did I know that it's that one? And because my V sub y is this direction, that's my V sub y. V sub y. So I have to look at above and below, which I'm talking, we are referring to the head and the tail of your arrow for your V sub y. So in this particular case, I'm talking about the area of a half circle multiplied by the distance between the centroid of my area, distance between the centroid of my area and my neutral line, and this would be my neutral line of your cross section, which means I have this certain distance right here, y sub bar. So that part is clear. And then I'll go to switch to
that
other
makes
one.
sense.
Yeah. So now let's go to the other one. So the other one, your shear direction, V sub z, is this one right here. That's your V sub z. If you are going to talk about above and below area, you are talking about heads and tail, which means I have to get the area either on the left or right side of this drawing right here. In this particular case, I have to get the area on my right side, which is entirely the whole circle here. That's the area of the entire circle, which is pi r square. Now I have to get the centroid of this circle, which is this center line right here. And I have to get the distance of that centroid to the neutral axis. And my neutral axis is this one, which coincides with my centroid, which means your Q will always be 0 at this point. So because this y bar right here would be equal to 0. I think I should, yeah. It's equal to 0.
Understand.
Yeah. So your V sub z would not contribute to your shear stress, even though it's a non-zero value. In this particular problem, it's 0. So technically, we can just up it out, assume 0. But this is something that if there's a value, let's say in your exam, you would see that this would not contribute to your shear. Any other question with that? And that's confusing.
Thank you.
Yeah, no problem. And that could be confusing to be honest. And you will need this concept in your machine design. You will need this a lot, I think. So because I experienced before that students come with me after taking this course, taking machine design, and goes back in with me and consulting how to solve those problems. Anyway, so that's for V sub z. So how can we now calculate for our shear? We almost forgot that we were calculating shear.
Excuse me, Professor.
Yeah, go ahead.
I just wanted to clarify before we moved forward. This, we're saying that the shear in the z direction has no effect on shear. That's specifically shear in the xy plane, correct?
Yeah, that is correct. Yeah, that's precisely correct. Yeah.
Okay. So for a problem like this, should we be finding like tau xz as well, or just tau xy?
Just tau xy. So in your exam, I'll specify which plane you're going to analyze, because normally for this type of analysis, it's just a 2D analysis of a certain section. But yeah, of course, you're right. But again, I'll just refer to a plane yx, or let's say xz. It could be xz. So for example, if you calculate point H, your plane is xz, but you're still in a 2D plane. So it's just a matter of assigning the axis. But that answers your question?
Yeah, it does. Thank you.
Okay, yeah, but we're not going to do 3D like the shear, like going out or inside the plane. Yeah, we're not going to cover that one. Yeah. Okay. So now let's discuss about shear. So we know that the shear stress is a function of your T, which is your torque. Oops. Yeah, I'm just checking what are the values we have. V sub y. So torque, V sub y, and V sub z. It's a function of torque, y, and V sub z. Now your torque, take note, it's producing a negative shear, as we discussed earlier. Torque is rotation along our x, which produces this downward force here at the edge of your K. And if we are going to imagine that, our y and x, and if that's our point K, so we are producing that shear, and that's a negative shear. So remember that this would be your positive shear right here. That's a positive shear. So your torque produces a negative shear, which means it produces TC divided by J. So it's a negative number. Now we know that your V sub Z is equal to 0, so that will contribute to your shear stress. Now how about V sub Y? So your V sub Y is going up right here, and we analyze it from the top right here. So your V sub Y has the following VQ divided by IT, and we have numbers for that. So that would be positive VQ divided by IT. And how did I know it's a positive number? Your V sub Y is pointing upwards, which means if I'm looking at my K right here, it's pointing upwards right here. So it's pointing upwards right there, which means it's contributing to a positive shear. So that's positive and that's a negative number. So if we're going to solve our shear stress, so that would be 900 negative 900 Newton meter. And then this is 0.02 meters divided by 251.3 times 10 raised to negative 9 m raised to 4 plus, I'm thinking if you can still see it later, but yeah, so I'm just going to write it down here. So that would be plus 18 kilonewtons. So that's your V sub y. Going to put here V sub y, 18 kilonewtons. VQ is, we calculated Q from the top, and this is the number for our Q. So VQ 5.33 times 10 negative 6 m cube divided by, so we calculated our I last meetings, it's 125.7 times 10 negative 9 m raised to 4. Now this is your T, which is 0.04. So your T is equal to 2 times your radius. So that's the width of your section. And that would give you a value of T is equal to, I'll put two numbers first, negative 71.6 plus 19.1 megapascals. And your tau is equal to negative 52.5 MPa. So you have two numbers here. You have your shear and you have your normal stress. So let's say shear. And your normal stress is on the top. Oops. So which is this one right here. Now we're not done yet because we have normal and shear stress. So the normal and shearing stress at point K. You can do a practice at home at point H. But the next question is the principal axis and principal stresses at K. And how do we do those principal stresses? So we just go back again to our principal stress equations, and then we solve the problem. So we have sigma x is equal to 107.4 megapascals. Sigma y is equal to 0. tau xy is equal to negative 52.5 MPa. And we can use method of equation. You're asked about principal axis, and normally for principal axis, you are asked to calculate theta sub b. Now you're also asked to calculate sigma 1 and 2, which are your principal stresses, minimum and maximum. And I can write the equations right now. So for letter B, or we're using numbers really just to make it consistent, we're using number 9. So we'll go for number 10. So for number 10, we are going to calculate this too. So for number 10, so theta sub b, or tangent of 2 theta sub b is equal to tau xy sigma x minus sigma y divided by 2. And then what you will get here is theta sub b is equal to, I'm not substituting the values. You can do this as a practice at home. We did this a lot in the past quiz 1 and 2. So we have theta sub b is equal to this number. Now I can also calculate my sigma 1 and 2, which are just basically sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 squared plus tau xy squared. Hope I don't miss anything there. And that would give you a sigma 1 is equal to 128.8 megapascals, and sigma 2 is equal to negative 21.4 megapascals. So that would be my principal stresses. So the next question there is your maximum shearing stress. So your principal stresses have different signs, which means I can calculate my in plane, which is just the radius of my Mohr circle. But let's say I'm going to calculate my maximum, which is my tau absolute max. So my tau absolute max, and I'm going to put this as 11. So for tau absolute max, take note that we have positive and negative signs for our principal stresses, which means they have different signs. So my tau absolute max, and if you can still remember this one, it's sigma a minus sigma b divided by 2, and that's the absolute value of that. And that's just basically your sigma 1 and sigma 2 on top, and that would give you a value of 75.1, and that should be megapascals. So those are the numbers that you're looking for when you're solving this problem here. But again, the critical part is the one wherein we have to deduce what's the effect of torque, what's the effect of moment, and all the other things right there. Question class. A question, another question. Okay, so that's the combined loads apart. Any one of you wants to clarify the effect of each individual PV to a certain point, K and H? I have 5 minutes, but I'm thinking if I should discuss the next topic, or I could probably discuss this more. Okay, I'll give you 2 scenarios right here. Okay, so let's say we have this particular part. Okay. And I'll find out on Monday if we to finalize the scope for midterm exam. But anyway, for quiz number 3, it's final. That's the scope. Whatever you can see from D2L, that's what it is. For midterm exam, whatever we finish by Monday, Monday next week, that's okay. I mean, that would be the coverage. So Z, and let's say this is Y. So let's say we have this axis. Of course, we have, let's say we have 2 points, point A and point B. Say point A and point B. Now we have different forces, so we can have our force P, which is perpendicular to our surface P. We can have our V sub Z, and then we can have V sub Y, and then we can also have our moment. So let's say we have a torque, so which is this torque right here. We have M sub Z, and then let's say we also have M sub Y. So we have 6 different numbers here: moments, torque, and forces right there. Now the question here is, what if I look at different points? Let's say at point A. And let's look at point A. So at point A, this would be our cross section here. So it's A. So we are particularly interested in this one right here. Now, looking at point A, so if you imagine the effect in normal stress, so let's say in normal stress, so normal stress is a function of your P. So it affects at point A, it affects your P affects the normal stress. How about the other forces? So it also affects. So if you imagine point A, it's also your M sub Y also affects your normal stress, but your M sub Z doesn't have an effect on A, because imagine if we are at point A, this is point A from M sub Z, and then if this is Y and that's your X, your M sub Z is like this. It's in the center, it's in the neutral, it's not compressing, it's not applying any tensile force, so it doesn't, your M sub Z doesn't affect your point A. Now, if you look at point B, it's the other way around. So your point B would be this one here on the top, that's Z, and that's Y. If you look at point B, your stress is a function of P and M sub Z, but not M sub Y. Because if you look at point B, if you're looking from the top, let's say from the top, so if you're at point B, looking from, let's keep this axis Y and X right here. So your point B is at the top, your moment should be X. So your moment is like this, which means your M sub Z is compressing or pulling the other parts. So that would be for M sub Z. So you can see the clear difference if you move your points from point A to point B, that this two right here would have a different effect. So how about if we apply shear? So this is for normal force. How about for shear? So point A. Let's look at point A. So tau at point A is, so again, if we're looking at point A, we are referring to this point right here. So that's A, and that's Z, and that's Y. Now, your torque would always be a factor for your shear, so I put torque right there. Now, how about the two other forces? So we have V sub Y, which is this direction, and V sub Z, which is this direction. Now, you can clearly see that your tau right here is a function of your torque and your V sub Y. And for point B, you can see that your torque is the other way around. It's a function of torque and V sub Z. And I think we're almost finished. So that would be this point right here. So you can see how it will change. It depends if you're looking at point H, point K, what moment you have to consider, what shear force you have to consider in order for you to calculate your number. So I hope everything is clear about combined loads. Let's start discussing deflection of beams on Friday. I'm going to stop the recording. Any other question?